Hi everyone, this is Dr. Diana Song Song. In this video lesson, we will be talking about Fibonacci number and the golden ratio. Okay, so first I want you to think about this problem. Form a rectangle using all of the squares given below. So what do the numbers here mean? This means that this square here has a side of length 1. This one is a square of side length 2. So meaning to say this one has an area of 4. This one has a side length of 5 and so on. So using all of these rectangles, I want you to create one big rectangle. Alright? You may pause this video for a while for you to be able to think about it. Okay? So I guess this is the, so if you pause the video, this is the answer to that certain problem. So here you have two squares of side length 1, so you put the square of side whose length is 2, and then this one has a side length of 3, so you put the square of side length 3 here. This one has a side length of 5 and so on, right? And lastly, the square whose side is equal to 8. Okay? Now, what are those numbers that appeared? So the numbers that appeared, let us just write down the numbers that we had. So we have 1, 1, 2, 2, 3, 5, and 8, right? So these are the first few terms of a sequence called the Fibonacci sequence. The Fibonacci sequence was invented by the Italian Leonardo Pisano Bigoglio. Okay, so the Fibonacci sequence was the outcome of a mathematical problem about rabbit breeding. So he observed a newly born pair of rabbits, one male and one female. They are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. Our assumption here is that rabbits never die and that the female always produces one pair, one male and one female every month from the second month on. Alright, so let's look at that in detail. So this is the 0 month. Okay, they are still babies here. So here we have one pair of rabbit. And then this is the end of month 1. Okay, so we just have one pair. But after the first month, according to our hypothesis, they can now, at the end of the second month, this pair over here will have this offspring. So we just bring them down here. They're just the same. So let's call this parent 1, parent 2. So they are still this, parent 1, parent 2. And this is their offspring. Okay? This is their offspring, O1, O2. Okay? And then on the third month, this rabbit here is this one. Okay? So they will produce another pair of rabbit. Okay, this is the new pair. Okay, this one will not yet produce, so we just bring them down here because they are just 1 month old. But then after, on their second month now, this one will have this offspring over here. And then for this one, where are they? Okay, so for this one, they are this. Am I right? And then this one, we just bring them down. And then this one, this is the new offspring, the newest set. Okay, that's just like new. Okay, in this one, this is the newest. Okay, in this case, this is the newest. Okay, did you understand the rabbit problem? So what happened here? So every month, so this is where the Fibonacci sequence appears. You have one pair, and then after that you have 1 plus 1, 2 pairs, and then you have 3 pairs, and then 5 pairs. So if this process continues, you will now have your Fibonacci sequence. Okay, so take note that the Fibonacci sequence, it is defined mathematically by this recurrence relation. What is the meaning of this? Fn equals f sub n minus 1 plus f sub n minus 2, where f1 equals 1 and f2 equals 1. Yeah, also there's it's also equal to 1. So what this is just saying is that we're just expressing our Fibonacci sequence. F1, this is the first term, F2 is 1, right? This one here, this formula here says that the next term is just the sum of the two terms before it. So that's why you have 2, okay? So for this one is F3, that's equal to F1 plus F2, right? And then for F4, F4 is equal to, okay, F4 is equal to F3 plus F2. So that's why you have 3. And then F5 is equal to F3 plus F4. So that's why you have 5 and so on. Okay. What I have on this side is just the same thing that we did. So what will happen if you have your the puzzle, right? If you will just continue that process, okay? Now let us find the pattern here. So what we want to do here is, I have here our Fibonacci numbers. What we want to do is we want to divide the term and the term by, we want to divide a certain term by the term before it. So for example, in this case, we will start with F2. This is my F1, right? F2, F3, F4, and so on. So for this one, we have F2 divided by F1. So that's 1 divided by 1. We get 1. For the next one, we have 2 divided by 1. So you have 2. And then next, you have 3 divided by 2. You get 1.5. 5 divided by 3, and so on and so forth. Okay, so let us see what will be the result. So we have here the results. What can you observe about these numbers here? They approach a certain number, and that number is our golden ratio. Now what is this figure saying? So I have here a square A, and then I have here a rectangle with length B and A. So therefore this side here is A plus B, this is A. Meaning to say, what we're doing there is we are dividing A plus B over A consistently, continuously, right? Because as you can recall, it's like we have your Fibonacci sequence. B is the smaller one, A is the bigger one, and then the next term is A plus B, right? Okay? So meaning to say we are doing A plus B over A. So this is like our Fibonacci rectangle. Okay, so we're always getting the quotient A plus B over A. Okay, so I have here the golden ratio. It's equal to 1 is to approximately 1.61803. Now the golden ratio is actually it's an irrational number. Its exact value is equal to 1 plus square root of 5 over 2. So take note that since this is an irrational number, it is non-terminating and non-repeating. Okay? Now, what is this Fibonacci spiral? Let us go back again to the squares that we had earlier. So this is my This is my 1 by 1 square. I have two of those, right? And then this is my 2 by 2 square, and then my 3 by 3 square, and so on. So what we're doing here is that let's start from here, no? So what are we doing here? What we're doing is that from one diagonal to one diagonal, we make like a quarter of a circle, okay? And then we just connect the points. So here and then continue here like that, okay? And then from here, diagonal to diagonal, diagonal to diagonal, okay? So can you see now what we have? This is what you now call our Fibonacci spiral. And take note that the Fibonacci spiral came, of course, from your Fibonacci numbers. And take note, where is the golden ratio here? Just like what we had earlier, the A plus B. This is this side here. Okay, this is 13, right? This is that right? 8 plus 5, 13. This is 5 plus 3, 8. Correct? So we have 13 over 8, right? 13 over 8. And then, for example, if we take a look at this one, this big rectangle here. Okay, what is this one? This is 21. This is 21 plus 13. This is 13. Sorry, 21. So we have 21 plus 13. Always the bigger number over 21. So again, the A plus B over A in this Fibonacci spiral will approach, this one will approach our golden ratio as you make your rectangles bigger and bigger. What we have here next is our Binet's formula. So Binet's formula enables us to find the nth Fibonacci number without using the recursion formula. Because for example, we want to get the, let me just change the color. Suppose we want to get the 100th term. If we use the recursion formula, that means we have to compute for all the 99 terms, right? And then keep on adding, keep on adding. So because of this formula, we don't have to do that. All we have to do is to plug it in the formula. So what the 100th term will be 1 plus square root of 5 over 2 raised to 100 minus 1 minus square root of 5 over 2 raised to 100 all over square root of 5. Of course, you may now use your calculator to compute for that. Let us just verify this formula in our table. Let's just try that for a small number lang. Let's say n equals 1 so that the computations will be easy. I will just remove this so that I have space to write our solution. Okay, so let's try for n equals 1. We have 1 plus square root of 5 over 2 raised to 1 minus 1 minus square root of 5 over 2 raised to 1 all over square root of 5. So let's simplify. We have 1 plus square root of 5 over 2 minus 1 plus square root of 5. Okay, I already distributed this minus sign and then eliminated the parenthesis all over square root of 5. What is that? The numerator will just be, we will be left with square root of 5 over 2 plus square root of 5 over 2 over square root of 5. The numerator is square root of 5 over square root of 5, which is equal to 1. That's our Binet's formula. Golden ratio and Fibonacci numbers are all around, they are around us. The next video will show you the nice thing about this golden ratio and the Fibonacci numbers.
We see that so many things flourish when they go to the golden ratio design and when they follow this sequence. Growing and expanding to the rate of the golden ratio spiral allows the maximum amount of rain to be directed down to the roots of many plants. And remarkably, when you study nature, you see the golden Fibonacci numbers like 3, 5, 8, 13, all of that again and again in the seed pattern spirals of plants, as well as in the number of petals. Next time you're bored and have a sunflower, try counting the number of seeds in the sunflower spiral, the golden ratio. Or maybe try something else with a spiral, like a pine cone or pineapple. So we could spend all day counting the seeds of flowers and plants and fruit. I mean, you get the idea. But we don't just see this golden ratio sequence on a small scale. This ratio is the mathematical sequence in the spirals of our storms, tornadoes, hurricanes. These all spin in this golden sequence, 1 to 1.6. Even the waves can be measured using this ratio. But it doesn't stop there. Modern technology continues to be mystified by the far-reaching scope of the golden ratio, from the alignment of the planets to the spirals of our Milky Way galaxy, as well as the spirals of other ratios in planets. Now let's take this closer to home. I want you to hold out your arm and look at the distance between your shoulder and your elbow, and then from your elbow to your fingertips. Notice how your elbow, from your shoulder to your elbow is 1, and then from your elbow to your fingertips is 1.6. Pretty crazy, huh? But it doesn't stop there. Now take that further. The distance from your fingertips to your wrist is 1, and from your wrist to your elbow is 1.6. Keep it going. From the furthest tip of your finger to the bottom of your fingers is 1, and from the bottom of your fingers to your wrist is 1.6. Now check out the spacing of your knuckles, 1 to 1.6. Are you getting freaked out yet? Think about this. The head to your belly button, 1, and then belly button to your feet, 1.6. From your toes to your knees, and from your knees to your hips, golden ratio. Ever wonder why your 2 front teeth are so much bigger? Golden ratio. The pupils of your eyes, I mean, you name it, your whole body is the symphony of the golden ratio. In fact, as you are listening to this video, the sound waves are passing through your ear in a perfect golden spiral. Scientists have discovered that the golden ratio pattern is necessary for the human brain, the neural system, our sense organs, and our lung system. The golden ratio sequence is even in the helix of our DNA, and it forms the very rhythm of our heartbeat pattern. This is pretty amazing if you ask me. The universe is an incredible place. And to think that these beautiful intricacies of the world all hang on a stacked razor edge with the incomprehensible fine-tuning of all these precise constants and quantities which allow the universe to begin to exist. I mean, it's unfathomable. No wonder we are naturally bent to worship a higher creative power. I mean, we are fearfully and wonderfully made, and we live in a universe that is designed and hardwired to be life permitting. I mean, speaking of which, I think it's interesting that the golden ratio also comes up in the ancient biblical text. Scholars have noted that when you consider design measurements of things like Noah's Ark and the Ark of the Covenant, the golden ratio is an exact match to the measurements. Pretty interesting. Okay, so we've seen how the golden ratio is embedded into our life and even into our own heartbeat. So naturally, it's going to affect our aesthetics and the arts. It is believed that the Greeks used the golden ratio to achieve ideal acoustics, and many instruments are actually designed with the ratio. When you look at the amount of black keys and white keys on a piano, it should be no surprise that you see the golden ratio, and that's because the musical scales and notes align with the Fibonacci sequence. So scientists, mathematicians, and artisans have been aware of the golden ratio and have been incorporating it into their architectural and artistic designs throughout history. For some reason, designs tend to look better when composed and designed with the golden ratio. Look at iconic ideal Greek temples like the Parthenon in Athens. You can see that they use the ratio again and again. Painters have also been incorporating the golden ratio into their artistic designs because it gives the composition a je ne sais quoi. Leonardo da Vinci was obsessed with it. So was Michelangelo. Even in the 20th century, you see ratios being used in painting, whether it be in the dimensions of the canvas or the placement of the focal point. And by the way, the golden ratio is one of the reasons artists don't like to line everything up in the center. But you don't have to go to Greece or to the Louvre to appreciate the golden ratio in human design. I mean, just look around your house or go to the grocery store. The golden ratio is used in product design, logos, and in branding all the time. It's a ratio that, for some reason, is pleasing on the eye, and it can be a great template for solving multiple design problems. I remember when I first started learning about the golden ratio, I began to see it everywhere. And it's really remarkable with how it comes up in nature and in the design world, and how artists can greatly improve their designs by using its sequence. So now that you know about this mysterious sequence that pops up again and again, now go out, and I want to challenge you to go and look and find places where you see this ratio. You don't necessarily have to take around a measuring stick, but take pictures and notice where you see this ratio come up in design and in nature, and I think you will be surprised. And perhaps even this newfound awareness, it might even change your life.
It was mentioned in the video earlier that the reason why photographers didn't always put their subject in the center is because they want to follow the golden ratio. So this is the phi grid. You use this in order to make sure that you get good pictures. So for example, if you use this and you take pictures and you want to make sure that you align your pictures in the phi grid, then you will be able to get nice pictures. So that's it. That's our lesson about Fibonacci numbers and the golden ratio and how we can see them everywhere in nature, in the galaxies, in the world around us. Thank you for watching my video. For more videos like this, don't forget to subscribe to my channel, and don't forget also to hit the bell button for notification updates. See you on the next video.